Welcome to another video on digital logic. This time what we're focusing on is Verilog. Verilog is the most popular language for doing hardware descriptive language, describing the behavior and expecting in the program we just describe the behavior, and then the computer or the Verilog compilers and the set of those will be used to create the circuits we need and the layout we need to be successful. The steps basically start from having a design, wanting to do a design, writing a code, compiling, simulating to test to make sure the design is correct. And then the next step would be to send it to be produced by one of the vendors, such as Synopsys, Intel, Xilinx is probably one of the biggest one. They were a company by themselves, now they're part of AMD. We're now gonna, in this video, we're gonna kind of have a conception, come up with the design we wanna make. We're gonna actually write the code to describe the behavior, and then we're gonna simulate it. And then we're gonna stop at that point. In order not to get too wrapped up in the whole thing, we use a simple device such as a D flip-flop. We describe its behavior and have the computer generated, and we use a simulation to test to make sure it's doing what we want it to do. We're going to write our code using a beautiful interactive development environment produced by ALDEC. Is a company that produces the interactive development environment that helps us write the code and simulate it in a very nice user-friendly way. There are many other tools available in the market, but this one is very nice. And also for education purposes, the ALDEC has been kind enough to provide their tool for a whole year free of charge for student and education, not necessarily student, but education use as a student version of it. To download it, you just go to this space and download it. Click on the free. It's going to ask you what your name is and what your address is. So far, I have been using this for many years. I haven't got a single ad or single spam or that kind of stuff from them. So I have great trust that they would continue to be the integrity of providing this as a service and not using it as a way of marketing things. Okay. So having said that, you go ahead and click on this free download and get it downloaded and start using it. It's a full feature product. We're only going to use it as more of an introductory to get us familiar with it. We're going to try to not go too deep in any single features of the product. Okay. So having said that, I have already downloaded this and is available for me. So I'm going to run it. And when it comes up, it does give you a little warning, say, if you want to do commercial uses of this to build something that sell, you really need to get a commercial license. We are doing it for education, so it's okay to use that for a year. Okay. So this is the screen that comes up. And if you look at the screen, just like a normal application, it's got some menu items at the top. And it's got a bunch of icons. Unfortunately, depending on the size of your screen, you may see some of the icons, you may not see some of the icons. Every icon can be functions that are tied to each icon can be activated from the menu. It's a little more cumbersome, but they're always there. So I'm going to, throughout this presentation, and I will use the menus to access all the features, so I'll make sure you guys have it as well. The only exception would be these buttons are always present, so I'm going to use these zooming and starting a simulation and all that here. Okay, so what this is, and by the way, one other really important thing is this console window where basically ALDEC is talking to you, the Active-HDL is talking to you and telling you what's happening. You know, that's where the system gives you messages. And so this is a very nice ID. You can do all your work here from starting your design all the way to simulation and testing your design. And even you can send it to the vendor through this device, but we're not going to do that at this point. So, oh, by the way, when you download this thing, make sure that you don't click on the vendor information or the FPGA library. I mean, there's no harm in it if you want to do it. It just takes a long time to download them, and we're not going to use it unless you want to build a chip. Okay. In that case, you just download that particular vendor's solution. The other thing I wanted to make sure you did that when you, after you download, make sure you go to the preferences, go to the access your design, and make sure all of these three are unchecked, and read, write, enable, read, write is all checked. So uncheck the top three, check the bottom three, okay? So that's all you have to do to make sure then everything is set up ready for you to go. Now we're going to start the design, and we're going to do this D flip-flop, relatively simple. It's got two inputs, one output. It's got a clock input, it's got a D input, and it's got a Q output. We all know what the function is. On the rising edge, Q becomes equal to D, and that's all we have to implement. Okay, we're not going to tell him what gates we're going to use or anything. We're just going to describe the behavior of the flip-flop and expect it to do its job. So now, let's see how we do that. So the first thing we have to do, we have to go here and create a new something. Okay, design is another word for our project. So when we are doing a new design, we're creating a project. Workspaces, if let's say I have 50 projects, or not 50, but let's say 10 projects going at the same time. Each one is a design. If I want to contain them in a workspace, that's a good idea to create a workspace. Now, remember that each level, like workspace, is like your office. In your office, you have one computer used by all your project, or you might have tools that use across all the projects, and it is in your office. Workspace works the same way. If you had tools and resources that you wanted to use across a lot of projects, then you put it in workspace. We're not going to do that. We don't really have those resources that we want to put in a workspace. So ours is kind of an empty room, if you will. So I'm not going to create that. I'm just going to start a new design. You have to design. I'm going to create it empty. You could, if let's say this was a continuation of another project that I want to bring all the assets from that project, I could say create this thing based on an existing resource file and things like that. But for now, we're just going to say, no, create an empty one. I want a brand new one's created. And then the next one says what language you want to use. Of course, we're going to use Verilog. We like C. This is C-like. This is the most popular language out there, Verilog. And we're not going to, that's what we're going to use. Vendors right now, we're not going to define any. We don't want the overhead of customizing for a define right now. But if you ever wanted to build for different vendors, different products, different technologies, you would put, and if you, since I didn't download the FPGA libraries and the vendor libraries, I don't have a lot of selection, but at least, you know, here are some names that you may have heard: Ultra, Chip Express, Intel, Lattice, Microsim, QuickLogic, Silicon Blue, Synopsys, and Xilinx. Or Xilinx is, I think, the bigger one of all of these guys when it comes to FPGA and things like that. But all of these are pretty successful companies in this space. Okay. All right. So you're not going to define any of those. You could just want to say Verilog, and you're going to move on. What do you want to call my design? Well, I'm building a D flip-flop, so the natural thing is for me to call it D flip-flop design. Okay. All right. Spell that would be good. Design, that's great. So you're going to create me a location. I like to have a directory, so all the files for this design goes to one directory, so I can manage it a little easier. It'll create 10, 15, 20, depending on what you're doing, files, so it's nice to have it in a directory. If you don't want the directory, you want to throw it all in the same directory. I don't know why you want to do that, but if you want to do that, you can check this, but that's not. Okay, so we are here, and this is a good place for it to put it. Is a what I've called as a DFF design is the name of my design. Sure, create it for me. Here, now I have an empty design created. So what do I do next? So the next thing I need to do is create something to put in there, which is done in the form of a file. All right. So how do I get my behavior described? I do that through a file. So I say add new, double click on this thing. It pops up. You can create with an empty file. It's going to be an empty text file, or we can use the wizard to do it. I think that for the first few times, wizard is easier for you to use. But once you have get hang of it, you probably faster typing it and will probably do a better job than that. There are other ways. I can start with the state diagram. You can start with a block diagram, but let's start with the code. That's probably the more effective way for us to do this. So we're going to start with the Verilog. Okay. So, okay, use the wizard. Wizard will create everything for me. So let's move right along and say what is next. Okay, and we say, okay, tell me what you want to call because it's going to create a file. What do you want me to call that file? Well, it's a D flip-flop. All right. And what do you want to call it? The module? I say, okay, it's a D flip-flop module. Okay, and so fine, that creates it. Nothing exciting. Now I can, this is basically, I'm drawing the system diagram. I'm telling what are the input and what are the output. I'm not really here, I'm not describing what it does. I'm just telling it how it connects to the external world. I'm just defining its external interconnections. So I say, okay, I know it's a D flip-flop, so I've got a D, okay? And it's only one bit, so I don't have an array index. If you have 50 bits, you could say 0 to 50 if you wanted that. But in this case, I only have D. It's one input. It's an input. That's great. And then type, always the inputs we say wire, unless somebody has a really, really good reason and insists it shouldn't be wire. Wire is the most common thing. What it is basically connecting 2 point. Wire is as it sounds. It's just a connecting mechanism from one point to another point, and that's all the wire is. That's what the input is connected to. Okay, so that's the type is wire. We'll do another one. We need to have a clock. Clock is once again an input, and with the type, once again, nobody's twisting our arms, so the clock wire is the right thing to do. All right. And then we do one more thing. We need to have an output, and we're going to call output because this is the flip-flop. We call our output the Q, which is the current state of the flip-flop. And on the output, we always define the output as a rich. Okay. Now you can see it created the system diagram. Okay. Before we go off of this, I want to point out one other thing. You also gives you a time scale. That all it means is that this simulation, the smallest unit of time is 1 nanosecond, 1/10 to the -9 second. That's the smallest unit of time you can work with. And the accuracy is 1 picosecond. So it could be plus and minus 1 picosecond. Picosecond is 10 to the -12. Nanosecond is 10 to the -9. So you're talking about an accuracy of 0.1%, 1/1000th of a point. So that's pretty nice. If you don't like it, you can change it. You go to time scale and change it to whatever you want. For introduction, I doubt if you ever need to do that. But if you're building devices that are different speeds and different things, you might want to speed it up or down or whatever the case might be. Okay, we're done. We've got everything we want clear, created. So this is kind of nice. I don't want to take a few minutes and show you. Anytime you write a piece of software, you really should be providing this type of information at top of your file. Who you are, what are the things you're trying to create, when was the program written, all of those kind of good stuff is very, very useful. And so you should have it. And then the description, you couldn't do the description, so we're going to do the description. The description, we are trying to do a rising edge D flip-flop. Okay, that's what we are trying to implement. Designing a rising edge D flip-flop for educational purposes. That's why we're doing this. So I might as well tell the world. I'm going to get rid of some of these comments. Remember, this is a C-like, so / just like C, and it's comment, and you notice it's green. The time scale is always up here with the little apostrophe starting it. module. My module is here. My inputs are in this, outputs are in this open close bracket parenthesis, D, Q, D, and clock. The semicolon is a little funny, but that's how the syntax works. So you have to have a semicolon at the end of every line, pretty much. And then this is how it does it. You can do that. It says Q is output, Q is a register type, and all that. But you don't have to do this in separate line. I think it's a simpler way. It makes it a little bit readable from my point of view. This is by bias, maybe, to say output is register and it's Q. Okay. This way, that replaces both of these lines, so you can get rid of both of these lines. Okay. And then if you had multiple outputs, you can line them up. Like for input, we have input is of the type wire, and we've got a D and a clock. Okay. And generally, I have a bias, and I don't know where I picked up this bias, but I find it easier if, when we organize this, have the inputs first and the outputs next. But I won't go through that and change it. But so you can move this up or down if you want it. All right. So far, all we've done is said what the input and output. We haven't said what happens inside the chip. As you know, this is where we start to do a functional definition for the flip-flop. Now, there are three types of blocks available to you. One is called the initial block, initial, begin, end, and whatever you put in between begin and end in the initial block, it gets executed once during the whole process, and that's it. Assign is completely the opposite, is that if once you say assign A equal to B, that's always going to be there, regardless of what else is happening, that's going to happen. And that's we can have that conversation on a different video. But the last one, that's the one we're going to use here, is always kind of, I find it to be more useful in some ways, because always I can trigger when do I want the assignments to happen by putting it in the sensitivity list. So I can say always, if I always with nothing, then it happens all the time. It becomes almost like an assignment. It's a little different because it doesn't, only time when things change, it does the assignment. But always add, I can really define. So I can say always add clock. So anytime clock goes up or down, anytime it changes, whatever I have between begin, which is like the squiggly bracket open, in a C, and end, which is squiggly bracket closed. Whatever I put in here, it gets executed when clock either goes up or down. This is a rising edge. I just want to look at them going up. So they have a thing called positive edge that allows me to say only execute when the clock is going up. Okay. Now, you know, the other thing I'm sure you've noticed by now, we've already talked about the fact that the comments are green and the keyword, all the keywords are in blue. So if your keyword doesn't turn blue, you misspelled it. So for example, I do this very often, just getting used to writing sentences. I do this. Positive edge with the P capitalized is seen as a not one of the two. I'm going to leave this error in here to show you something else. So I've written a code. I have not finished the code yet, but I'm going to leave that error. Just remember that. And then what I'm going to do, I'm going to just say what this thing does. And I'm going to say, okay, this one, basically the job is when the clock goes from low to high, I want you to make an assignment of D to Q. Okay. Now so that's all the flip-flop is, right? Now you might ask, hey, that's a funny looking assignment, this less than equal, and say, yeah, it's funny looking, but it's a very useful one. This is referred to as a non-blocking assignment. Okay. What that means is that if I have 10 of this assignment or however many assignments I have in a row, they all get executed exactly at the same time. The second item doesn't have to wait for the first item to get executed. So as opposed to versus, versus this, which is a regular assignment or blocking assignment. That's what you're used to. The blocking assignment says, okay, if I have 5 of these or 10 of these, the first one finishes execution, then the second one starts, just like C. And one statement gets done, then the second statement gets done, and you go down the list. Okay, so we're pretty much done. That's all there is to it. So this is a D flip-flop. I never talked about gates. I never talked about anything. I just explained that on the positive edge of the clock, it's got to make the assignment, and it does it, and therefore I have a D flip-flop. Okay, now what do I do now? Great, now you have described it. What do I do? So the next step for you is to do a compile all. Okay, and the reason I put that capital P in here, I wanted to show you that this has got a nice little feature where when you make a mistake, it'll tell you in the error messages. So don't ignore the red stuff in the console. So look at it. It says, hey, in this file of yours on the line 30, column 19, something bogus is happening. You go check it out. So we go up here, and sure enough, this is supposed to be a small letter, and we are good to go. Okay, so now I'm going to compile again. So you always, once you finish with your code, you always have to do a compile to make sure you can compile and everything looks okay and all is good. So it looked like we were successful. We compiled everything. We have no error, no warning. Life is good, and we are on our way to. Actually, our design is done. We're done. We know what the inputs and outputs are. We know what happens inside. So we're pretty much done. Now we got to test to see if this thing really does work. In order to do that, you have to do a few things. Once you compile it, you got to initialize your simulation. That's the next step. When you initialize your simulation, simulation says, where do you want me to get started? Now in C, you used to have a main, and in all the compiler knows, and all the when you run it, and they know you got to start that main. In this case, they don't have that main that everybody writes. So it's asking me basically by saying select the top level, where should I start? That's what it's asking. You say, okay, this is my design, and I remember I called it the flip-flop module. So start in the modules are like functions. Start at the flip-flop module. So I say, okay, let's go ahead and start there. Apply, okay. And there it is. It's telling me all that life is good at 9:37 p.m. on Tuesday, May 31st. Simulation has been initialized. You're ready to simulate. Okay, if I'm going to simulate, I've got to come up with some inputs, put it in, and watch to see what the output happens, right? That's what simulation is all about. So what I'll do is go create a waveform. You can create many different things, but waveform is probably the easiest thing for us to do. So I go under File. By the way, you can here, if you have this, you can click this one and get it as well. But what I'm going to, oops, that one, no, this one, new waveform. Okay, but let's go ahead and go to the menu. You go to the menu, new. And then you say new, what do I want? I want a waveform. So I'm going to click on the waveform, and notice you also get a little menu item pops up here, which you didn't have before, for if you wanted to do something with it. Okay, so what you could do now that you've got this waveform up, if you're not on a struct here, go ahead and go there. That's what you do, structure, so you can see all the inputs and outputs. And you're going to say, okay, let's go ahead and grab all of these. Just you select them and you drag them and drop them in here. That's all you do. And they pop up. Now, once I said, I kind of like my clock, you don't have to do this, but I kind of like my clock to be the first thing at the top of the list. So I just drag it and drop it there. And I want my input to be next, and I want my output to be third. Maybe I'm being picky, but that's all right. Might as well. It lets me do it, so I like to do it. And the values basically say, I don't know what you're getting here, and you haven't given me any values for clock and D. So that's what it says. So now we got to give it some value. So you just right click on this and set stimulus. So you can call this whatever you want. It really doesn't matter. Okay. And by the way, this you can also get from menu. It would be this guy if you don't want to go through the process I'm going through, but I kind of. As I said, in different screens, you get a different configuration of those icons. I always seem to feel like I'm searching for it when I'm on laptop or regular computer or whatever. They seem to be moving around, but the menus always stay the same. So I'm going to move the menu. I like to use clock for everything. Inputs, clock, use clock. So I'm going to start with a clock with certain speed. This way, I'll use 100 nanosecond speed. That's great. So, okay, that is, and by the way, it's pretty fancy. You can change the duty cycle. You can change the offsets. You can do all kinds of stuff here. But for now, we just worry about period. So the period is 100 nanoseconds. So each cycle completes in 100 nanosecond. So that's what the clock is. Now, the D, I'm going to use a clock as well. Remember what we do to set stimulus. And we say, okay, 2, fine. And I'm going to, instead of being 100, because if I set it at 100, they move at the same time. I want to see what happens when the rising edge comes up and D is 0. What happens when the rising edge comes up and D is equal to 1, because I want to see both cases to make sure this flip-flop is really working. So, and typically it works across the board for all things. If you just make this one double the clock, and then if you have another thing, make that next one double this one, and then double them every time, you get pretty much all the possible cases on your waveform, because you're really building a truth table if you think about it. So, by the way, it does provide all different ways of be my guest for one of your times when you have, just experiment with different modes, different types of input, and see which you might come up with a better one. Okay, so I have a simulation set up, so now I can run this thing. To run it, they have little icons here. I can run it forever until I stop it. I can run it until 100 nanosecond, or I can run it 400 nanosecond. 100 wouldn't be enough. I at least want to run it for like 10 clock cycle to see what happens, okay? So then 1000 nanosecond, that's 10 clock cycle. We should be in pretty good shape. And I'll go ahead and run it for that much, or run until, let's do run for that long. And this is what comes up. You can use these zooming techniques, zooming capabilities. There are all kinds of zooming stuff. Let's just do a straight up zoom. So what are we looking at? Okay, so the clock is doing rising edge clock. So let's go to the beginning of it. So this thing pulls us to the beginning of it. It says, I don't know what Q is because I don't know where we started. Once this rising edge comes on and this D is equal to 0, then it says, okay, 9 or Q is 0. Then rising edge comes up again. Rising edge comes up here. But this time when the rising edge comes along, notice that the D is high, so the Q goes high. You see that? And then later on, when we get to a place where D goes low and the rising edge comes along, Q goes down. Oh, sure enough, we built ourselves a rising edge D flip-flop. Now we can get fancy and build more sophisticated stuff, but now you know exactly how these things work. Okay. The simulation, you can save these graphs. If you're reporting on these experiments, the two crucial items would be a copy of this, so people know what your design, this is your design, and a copy of this. And both of those you could do by file, copy file. Oh, maybe you can, or maybe it's edit, select all, and then copy, and then it will take the whole thing. And the same thing here. You can do edit, copy, and take it all. Okay. Let's see, that's about it. So what have we done? We've taken Active-HDL, which is a Verilog IDE in an active development environment, and we've taken a design, simple design, the flip-flop, from beginning, creating a new file, putting it in there, and then compiling it, initializing the simulation, and then finally doing a waveform showing the inputs and the outputs coming out of there. Okay, and all of this are here available to you. That brings us to the end of this video. Hope that's been helpful, and thanks for watching.